Here we have the code for a queue implemented using an array as the item store. Now you'll recall from the slides that this is actually a significantly more complex implementation than a queue using a linked list. Now we start by allocating the array of items that we're going to use to store. Now I allocated an array of 0 items, and this means I don't need to do null checks later on, and I can just do length checks each time I'm adding. Size is the number of items currently in the queue. Size will always be less than or equal to the capacity of the array. Head is the index of the first item in the queue. This is the oldest item. It's the one we intend to return next time dequeue is called. Tail is the index of the last or the newest item in the queue. This is the last item that was enqueued. So let's take a look at enqueue. And as you can see, it's substantially longer than the previous implementation using a list. So the first thing we do is we check, is the size of the queue equal to the number of items that we can store in the array? And if it is, that means we need to grow our array. Now this could happen because it's the first item we've enqueued and our array has a size of 0. Or it might be because we've enqueued so many items that the array became full and now we need to grow it to put one more item in. We make that determination right here. If size is 0, we'll allocate an array of 4. Otherwise, we'll double the size of the array. We then actually perform the array allocation. Now, if size is greater than 0, we need to copy the items from the current items array to the new array. Now recall from the slides that we can't just copy the items from array index 0 to the end of the array. Rather, we need to copy the items from the first or head item of the queue to the tail item of the queue. And we might need to wrap from the end of the array back to the beginning of the array as we do this. And it's that wrapping part that we check for here. If the tail of our array, which is the last item we inserted into the array, is less than the head of the queue, which is the oldest item in the array, well, that means we must have wrapped around, because that means that head, for example, might be array index 7, but tail is array index 3. So the queue runs from array index 7 to the end of the array, and then from array index 0 to array index 3. So what we're going to do is first copy the items from the head to the end of the array, and then copy the items from 0 to the tail. Once we've done that, all of the array items have been copied from the old array to the new array, with the wrapping all accounted for. If we didn't need to wrap around, all we need to do then is just copy the items from head to tail. Now, regardless of the state, we've come to a point where all of the queue items are in the new array. And a nice side effect of this is that the head is at index 0 in the new array, and tail is at the new target index that we wrote to. And then, as we saw on the slides, the last thing we do is we copy the new array over the old array, and we update our tail pointer. And now we can add the new item into the array, increment the size, and enqueue is complete. That's quite a departure from our previous version of enqueue using a linked list. That had a single line of code which just added the item to the end of the list. But linked lists don't need to worry about wrapping or efficient storage. We don't want to waste space that we've allocated, so we need to do the extra work to make sure we make the best use of it. Now dequeue is a little bit simpler, and this is because dequeue never has to worry about growth. It only has to worry about shrinking. So what dequeue is going to do is store off the value. This is what we're going to return to the caller. Then we're at one of two cases. If head is at the last index in the array, we need to wrap all the way around so head is at 0. Otherwise, we need to move head forward 1. So think about what I mean here. If we had an array that was 4 items long, and head was at index of the 4th item, which would be index 3 in C#. When we pull that item out, index 3, or that 4th item, is no longer a valid item in the queue. So we need to move the head pointer forward. But we can't move it forward beyond the bounds of the array. We need to wrap it back around to the 0th index, or the first item in the array. We then decrement size because we've removed an item, and we return the value. Everything else is pretty straightforward. Peek simply returns the item at head, count returns size, and clear simply resets the values to their defaults. Size is set to 0, head is set to 0, and tail is set to 0. And finally we have the enumerator. And here again the enumeration becomes a little bit more complex than what we saw when we had the linked list. But this is pretty much the exact same logic we saw during the enqueue growth period. Notice we have these 2 loops and then a 3rd loop, and they look quite similar to these loops here. What we're doing is we're returning the values in queue order. In queue order is from head to end and then 0 to tail, or head to tail. And that depends on whether or not we're wrapping around, as we are in this case, or whether we're just enumerating linearly without wrapping around the array, which we are in this case. So it's not incredibly complex, but it's a heck of a lot more complex than just returning an enumerator from a linked list structure. And then the other get enumerator will just defer to the one we wrote. So as you can see, an array implementation is quite a bit more complex than a linked list implementation. But it comes with the benefits that arrays have over linked lists, which includes data locality and performance gains, as well as reducing the overall number of allocations and incredibly fast enqueue and dequeue times when there isn't an allocation being performed. So I hope it's clear why array-backed stores are quite popular, and in fact are the default for many queue classes implemented in the real world.